All right, folks, we're going to go ahead and get started. We've got two sections to cover today. We're covering 8.3, which is trigonometric form of complex numbers, and then we are starting to take a look at polar graphs and equations, okay? So I'm going to go ahead and share my screen so we can all take a look at those notes. All right, there we go. So 8.3 is a section called trigonometric form for complex numbers, okay? And really it's an introduction into different coordinate systems that we can use. So in pre-calc, we learn a few different ones, and you'll revisit those again when you get to Calc 2. And then in Calc 3, you actually learn a lot of these coordinate planes, but instead of being a plane, they're actually in 3 dimensions, okay? So that's really what we're kind of getting set up for. So on the left here, we have a Cartesian coordinate plane, okay? And so these are just a bunch of points that we know how to graph. Like if I said graph the point 2, 4, you would know how to graph it. Or if I said graph the point -5, -1, you would go -5 to the left, you'd go down 1 unit, and you'd end up right here at the point -5, -1. And that's something that we know, okay? Now, in terms of the complex coordinate plane, what we have is instead of having an XY axis, we have a real axis and we have an imaginary axis, okay? And so what we're graphing is not a coordinate like 2, 4 or -5, 1, but rather we're graphing something that looks like this: A plus BI, okay? And the A is the real part. So whatever number does not have the I, that's the number that we plot side to side. And then B is the number that is the coefficient for I, and that gets plotted along the imaginary axis. So if I wanted to plot the point 2 plus 3i, like right over here, I would go over 2 units on the x-axis, and I would go up 3 units on what looks like the y-axis, but we call it the imaginary axis, okay? So the first number tells you which direction to move side to side, and the second number tells you which direction to move up and down, all right? So let's take a look at distance on both of these planes. So on the Cartesian coordinate plane, or our XY plane, we can think about distance as the square root of your x value squared plus your y value squared, okay? Really, it's a dressed up Pythagorean theorem where you solved for the hypotenuse, okay? And so, for example, let's choose this point up here. Let's say we're looking at -5, 6, okay? So if I want to know how far is that point from the origin, then we would plug in -5 in for the x and 6 for the y. And this would give us the square root of 25 plus 36. Or what does that give us? 50 root 61, okay? So if I bring it back to the graph, what that means is from the center to this point, that distance is the square root of 61. Now, we can do something similar to try and find the distance on the complex coordinate plane, okay? And when we do that, when we're finding our distance, we're gonna take the horizontal component and we're gonna square it, and we're gonna take the vertical component and we're gonna square that. So if we want to find the distance to, let's pick this point down here, okay, we would plug in 2 for the x, we would square it, that's the horizontal distance, plus for the vertical distance, we would plug in a -3 and square that. And that would give us the square root of 4 plus 9, or the square root of 13, and that would represent this distance right here, okay? So even though they're called different names, Cartesian coordinate and complex coordinate plane, they function very similarly in that we have sort of a horizontal situation and a vertical situation to deal with. And that helps us locate any points we're interested in. Now, this distance on the complex coordinate plane is also referred to as the absolute value of the complex number, okay? So this absolute value is the same as this idea of distance on the complex plane, okay? We tend to use these bars here, that absolute value, to help us denote the fact that it is distance. And then this formula right here is just what we talked about earlier, the square root of a squared plus b squared, okay? All right. So let's take a look at what we mean when we say the trig form of complex numbers. So what we're going to learn in a little bit is something called the polar coordinate system, okay? And so this is sort of a preview of that. But with the polar coordinate axes, what we have is we don't just have an x and a y, but rather we define things with a radius, r, and an angle, theta. So we see radius, which happens to be the same thing as distance that we just talked about, and we have an angle. And together, those define a point. So for example, if I gave you the point, and it'll be in the form r, comma, theta, okay? Let's say that I gave you 3, 3 pi over 4. If I wanted to graph this point, here's what I would do. I would go to the angle first, okay? So I'd find 3 pi over 4 on the grid. And then from the center, I would go out 3 circles. So I'd go out 1, 2, 3. And that point represents 3, 3 pi over 4, okay? Now, any polar or any complex number can be written in a polar form. And so if we have a complex number written that is a plus bi, then we can say that the radius is like the distance that we talked about a few minutes ago. And theta is the angle that tells us where to stop. Then we can write, instead of writing a plus bi, we can write it as r cosine theta plus I sine theta, or we shorten that to be r cis c I s. Those 3 letters make up this cis. Okay. So I feel like sometimes this sounds more overwhelming than it is because there's a lot of new notation, but let's jump right in and practice converting between a complex number in rectangular form to polar form, okay? So we've got example 1 here. Convert -4 plus 4i to trig form or polar form. That means that I have z equals -4 plus 4i. That means that my a is -4 and my b is +4. Okay? So if I want to write this in trig form, I need to come up with the radius or the distance, and then I need to determine the angle to fill in for the theta. So I need 2 pieces of information. Okay. So first, I'm going to find my r using this equation, the distance equation. So r equals the square root of -4 squared plus 4 squared, which gives me the square root of 16 plus 16, or 32. Okay. And that is the same as 4 root 2. So everywhere where I see an r, I can replace it with 4 root 2. Right? Now, the only other thing we need to find is our theta. We need to find our angle. And so to do that, I'm going to go ahead and sketch where this point is on the complex plane. Okay, so if I plot the point -4, 4, what quadrant is that point in?
Quadrant 2.
Quadrant 2, good. So I got -4, 4. And I'm going to turn that into a triangle. So this is 4 units up, -4 units to the left. How can I find that angle given those 2 sides?
A squared plus b squared equals c squared, and then you would just get the no, wait, never mind, I need to think some more.
Okay. Yeah, I think if we do a squared plus b squared, we're going to end up with the hypotenuse, which is not what we're looking for. But how do I find this angle?
Does it have something to do with the fact it's the right triangle?
It sure does.
Tangent to Pluto?
Yeah, we're going to use tangent because we have the opposite side. We have the adjacent side. So to find theta, we can just say it's the inverse tangent of opposite over adjacent. Okay. And so that might also be an angle we know from our unit circle. This angle is 3 pi over 4. And so everywhere I see the theta, I can replace theta with 3 pi over 4. Okay. And so the trig form of this complex number is 4 root 2 cosine of 3 pi over 4 plus I sine 3 pi over 4. Okay, that's one way of writing it. Another way we could write it is we could shorten it to be 4 root 2 CIS of 3 pi over 4. And again, that CIS comes from the cosine, I, and the sine. Okay, that gives you that CIS, right? So either form there is acceptable, all right? Now you just have to remember how to find the r and to find the theta. So let's practice that one more time. We've got, in this case, z equals 2 plus 7i, okay? Now, I know that I need to find my r, and I need to find my theta. And so if I go ahead and find my r, I'm going to take the square root of 2 squared plus 7 squared, which is going to give me the square root of 4 plus 49, which is 53. Okay? All right, so let's find that angle now. Let's draw a picture. What quadrant is this angle going to be in?
1.
I'm going to be in quadrant 1. Very good. So I'm going to go over 2 and up 7. And so I can write theta as the inverse tan of 7 over 2. Now that is not a nice angle on our unit circle. So it's okay to leave it like that if it's not a nice angle, okay? You could just write this as cosine of arctan of 7 over 2 plus I sine arctan of 7 over 2. And this one would probably be much nicer if we wrote it in the abbreviated form. Okay. So that's one example where it is a nice unit circle value and one example where it's not a nice unit circle value. All right. So when we're converting, it's important to know how to convert both ways. So we knew how to go from rectangular to polar, but now we need to learn how to go from polar back to rectangular. And so what we're going to do is we're going to reverse the process, okay? I know that 12 is my r. And I know that my theta equals pi over 6. Okay. So what that means is I have a situation where if I drew the diagram, I would go pi over 6, and then I would go out 12 circles, and so that would give me a point like right about here, where the hypotenuse, where the hypotenuse is 12. And this angle is pi over 6, okay? Now, I need to find x and y, or consider them as sort of your A and your B. So this bottom side we could say is A, and the vertical side we could say is B. So how can I find A and B given what we know about right triangles?
Is it going to be c squared? I mean, well, a squared plus b squared equals c squared. Is this one where we find the sides?
Yeah, but I don't think you have enough information to solve it that way. I mean, that's not incorrect, but I don't think we have enough information to find A and B.
Inverse sine and inverse cosine?
Yeah, we could use our other trig functions to kind of help us find a side, right? So trig functions aren't just for angles, they're also for sides as well. And so I could say that sine of pi over 6 equals opposite over hypotenuse, right? And I could solve for B. And similarly, I could say cosine of pi over 6 equals my adjacent over the hypotenuse. And that's going to help me solve for A, okay? So let's use our unit circle values. I've got this as √3/2 equals b over 12. And that's going to make b equal to 6√3. Okay. And if I do the same thing with, oh, that's not 3/12, it's 1/2, sorry. That's going to give us just 6, but with this one, we'll get √3/2 equals a over 12, and this is where we'll get a equals 6√3. Okay. So you've got your a, you've got your b, and so to put your number into rectangular form, it's got to be of the form a plus bi. So that's going to be 6√3 plus 6i. Okay. All right, I'd like you guys to try number 4. Start by reading it over and then drawing a diagram and kind of seeing where that takes you, okay? But your goal is to find A and B very similar to how we did for number 3. All right, how do we find our A and our B in this case?
B is 5, A is 12 because of tan 5/12.
Love that. Okay, so tangent gives us opposite over adjacent. And B is our opposite side, so we know B is 5, and A is our adjacent side, so we know that's 12. Good. And this also happens to be one of those nice right triangles, right? 5, 12, 13. And so now that we have our A and B, we can write Z as A plus BI, or 12 plus 5i. Okay. So all that trig stuff that you learned in trig, definitely useful. Got to know that unit circle and really understand like what the different sides are in relation to each trig function. Okay. All right. So let's take a look at one application of complex numbers. So one application of complex numbers is that we can multiply them or divide them, and we actually have shortcut formula, okay? So this assumes that we have two complex numbers, right? We'll call the first one, sorry, my technology is being a little slow today. All right, let's try this again. Okay, so we've got two complex numbers. The first one we're going to call Z1, and that is R1 CIS1. And then we have another one that we're going to call Z2, which is a second R2 cosine theta 2 plus I sine theta 2. Now, if you want to take Z1 and you want to multiply it by Z2 in polar form, then you're going to take the two R values, the two distances, and you're going to multiply the distances. But the angles, we're not going to multiply them, but we are going to add the angles. Okay, so we multiply the distances, but we add the angle. That's a shortcut for how we multiply complex numbers. Now, on the flip side, if we have one complex number and we want to divide it by another one, then we're going to take the distances and we're going to divide the distances. Okay. And instead of adding the angles, we're going to subtract the angles. All right. So let's put these into practice and see what they get us. All right, so example 5 says, find the product and quotient of the complex numbers, all right? So they're already in polar form for us. Now we just need to follow the formula. So if we have Z1 times Z2, that means we need to take the distances, 3 and 5, and we need to multiply them. And then we're going to take the two angles, pi over 4 and pi over 6, and we're going to add them. Okay? So this will give us 15 cis. And when we add them, we have to make sure we have a common denominator. So we've got 3 pi over 4 plus 2 pi over 6, or sorry, 2 pi over 12. And so this gives us 15 cis 5 pi over 12. Okay. So you got to think multiplying the complex numbers means you multiply the distances, you add the angles. That's it. And if I ask you to divide those, Z1 divided by Z2, let's take our numbers and we divide those distances, but our angles, we're going to subtract those. And so that gives us 3/5 cis of pi over 12 once we combine our fractions after getting a common denominator. Okay. So nothing super special here, just a good formula to know that allows you to multiply and divide more easily with complex numbers. So why don't you guys try this one? Try example 6. All right, so we've got degrees this time, so there's sometimes a little bit less work, but practice using the formulas to find the product as well as the quotient of Z1 and Z2. All right, so if we multiply Z1 and Z2, we should get 8 cis 246. And if we divide Z1 and Z2, we should get 1/2 cis 180. Okay. Any questions about the formulas? All right, so let's add on to this. We know that a complex number can be written as r cis theta in trig form or polar form. We know that if we multiply two numbers, we can multiply the distances but add the angles. And we know if we divide two numbers, we can divide the distances and subtract the two angles. So this next section talks about finding the roots and the powers of complex numbers, okay? So to find the powers of complex numbers, we can use the following formula. If we have r raised to a power, then we're going to raise that number to the power. And we're going to multiply the angle by that power, whatever that power is, okay? Now, this rule is also called de Moivre's theorem, okay? And it's just, think about it like a shortcut instead of foiling everything out, because nobody likes to foil more than 2, really 3 times, okay? So example 1 would be asking you to foil 5 times, which seems kind of excessive. So instead, we're going to use de Moivre's theorem to help us find the power of that complex number more easily, okay? So let's plug things into our expression or into our equation. So my r value, what is my r value here?
Is it going to be 1?
R is not 1, no.
Square root of 2.
Square root of 2, yes. How did you get that?
By squaring 1 and adding them together, and then square rooting it.
So this is in a plus bi form. You need to get it into the r theta form in order to use the formula, okay? So let's get this into r theta form. So we know that r is the square root of a squared plus b squared, which is the square root of 2. And we also need to find our theta, which will be the inverse tangent of 1. And what angle is that in radians?
Pi over 4.
Pi over 4, good. Okay, so once we have our r and our theta, let's rewrite this to be root 2 cis pi over 4, okay? Now we're raising this to the 5th power, and now we can use de Moivre's theorem, okay? So de Moivre's theorem says that I'm going to take my r, I'm going to raise it to the 5th power. So root 2 to the 5th power. And then I'm not going to take pi over 4 and raise it to the 5th power, but I'm just going to take pi over 4 and I'm going to multiply it by 5. So whatever my n is, I multiply that. So what does that give me? It gives me 2 to the 5/2 power cis of 5 pi over 4. Okay. And 2 to the 5/2 power, what does that give us? Let's see, 2 to the 5th. And then I'm going to take the square root. So this is 2 and 2. So 4 root 2 cis 5 pi over 4. Okay. Now, one of the big things in math is whatever version your question gets asked in, that's the version your answer has to be in. So right now my answer is in trig form, but my question was asked in rectangular form. So I have to go back and put this back into my a plus bi form, okay? So how do we do this? We return to a plus bi form. Well, we're just going to expand. So 4 root 2 cosine of 5 pi over 4 plus I sine 5 pi over 4. And I'm going to replace those cosines and sines with values for my unit circle. So cosine of 5 pi over 4 is negative root 2 over 2 plus sine of 5 pi over 4 is negative root 2 over 2i. And I'm going to distribute so I can see my a plus bi. And that's going to give me a negative 4 minus 4i. Okay. So instead of doing 1 plus I to the 5th and multiplying it together 5 times, using these 3 steps, we can still get to the same answer. And so it's not necessarily easy, but maybe it's the lesser of 2 evils in that I don't have to FOIL 5 times and maybe make a sign mistake here or there, or have things cancel that didn't actually cancel. So that's a good application of de Moivre's theorem, okay? Any questions on this example? All right. So I'm going to have you guys try the same thing for example number 2. Okay. So think about what you need to do to get this expression. Instead of FOILing it out 7 times, how do we use de Moivre's theorem to get us to that same answer? Okay. All right, so we should have our r equals 2. What are folks getting for the theta?
Would it be pi over 6?
What do we think? Pi over 6? Anybody confirm or deny that?
I got pi over 6 too. It was equal to like 30 degrees pi over 6.
Okay, so that is our angle. And so now we have it in the r theta form. And now we're ready to use de Moivre's theorem. So if we want 2 cis pi over 6 to the 7th, we're going to have 2 to the 7th. And we're going to have cis of 7 times pi over 6. Remember, we don't raise the angle to the power, we multiply that. Now, let's see what we get. So 2 to the 7th, what is that? 64?
128.
28, I'm off, yeah. 128. So 128 cis of 7 pi over 6, okay? Now, because our question was asked in rectangular form, we got to return to the a plus bi world, okay? So we're just going to expand this, replace our trig values, and see what we get. So cosine of 7 pi over 6 is -1/2 plus -√3 over 2i. And so that's going to give us -64 minus 64√3i. Okay. All right. Any questions on de Moivre's theorem? Okay. So.
Is that I in the square root?
No.
Okay. Just needed to verify. Thank you.
Good question. Good question. I know sometimes it gets a little long when you're writing it, but the I is not under the square root. And actually, to address that point, sometimes you'll see this written like this. Oh, sorry. -64 minus 64i root 3. So I think we're so used to having i's at the ends, but sometimes, because a lot of folks who are working with this have the same question you have, like, is that I under the square root? If you move it in front of the square root, then it's not a question anymore. So that's why sometimes you'll see the I in front of the radical, okay? And you are welcome to use that notation if that makes you feel more confident that, like, you know it's not inside the square root.
Thank you.
You're welcome. Okay, so now instead of looking for powers, we're going to be looking for roots of complex number, okay? So when we are looking for roots of complex numbers, we have to read the question very carefully, okay? So example 3 says find the cube root. Cube root means the root is 3, okay? What that means is we are going to have 3 answers, okay? Now, if I said find the square root of something, how many answers would you be looking for?
2.
2. And if I said the 4th root?
4.
4, okay? So the number that it says there, so if it says cube root, you know at the end you need to have 3 answers. If it says square root, then at the end you're going to have 2 answers. But if it says 4th root or 5th root, then you need that many answers, okay? So here's what we're going to do. This formula, if I want to find the cube root of this, then I'm going to have z to the 1/3. okay? Because 1/3 is the same as the cube root. Now, if I take a look at what the formula looks like, okay? So z to the 1/3 means I'm going to take my r and I'm also going to raise it to the same power that I raised my z, okay? So if it is a cube root, then I'm going to raise it to the 1/3 power. If it is a square root, I will raise it to the 1/2 power, okay? And then my CIS, thoughts on what we're going to do with that 3? Any ideas?
Multiplication.
We think multiplication. Anyone else got an idea?
I do, but it's probably wrong.
What do you mean it's wrong?
Because since it's being to the 1/3 power, wouldn't it be the same as division? Like so for the 2 pi over 3, wouldn't we be taking, it'll be cubing that angle, so wouldn't we basically have to cube the angle? So raise it to the 1/3 as well?
No, actually. So whatever we do to the angle is not the same as what we do to the distance. Okay, so that's got to be a clear distinction. What we do to the distance is different than what we do to the angle. All right. So in the past, we've seen that we multiply the distances, but we add the angle. Where we divide the distances, so we subtract the angle. All right. So here, if we're raising a distance to a power, then we do need to divide by that 3, or we could think about it as multiplying by 1/3. Okay, so we're going to take our angle, we're going to multiply it by 1/3. No, it's not. Okay. And in addition to that, so like I said, if I know I'm going to have 3 answers, here's what I need to also have in here. Plus, kind of like our general solutions from the other day, 2 pi k, but we're also going to divide this by whatever root we're looking for. Okay. So this is our general form. If we have 3 answers, we're going to find them by plugging in 0. We're going to plug in 1, and we're going to plug in 2. Okay. So let's see what we get when we plug in 0. We will get 2, because 8 to the 1/3 is 2, cis 2 pi over 9 plus, what am I adding to it?
Would it just be 2 pi over 3?
Nope. Think about what you're plugging in.
Is it undefined?
It is not undefined, no.
0?
Yeah, it's 0, right? 2 times pi times 0 gives me 0. And so 0 divided by 3 gives me 0. And so I can write the first root as 2 cis 2 pi over 9. But whoever said that you're adding 2 pi over 3, that would have been correct for the second one, because when I plug in 1 for k, I get this. All right. And so, of course, if we want to add these, we need a common denominator. So that's 2 plus 6, which give me 8 pi over 9. And then to find the last one, I plug in 2 for k. So that'll give me 4 pi over 3. And that will, let's see, when we get a common denominator of 9, 12 plus 2 is 14 pi. Okay, so you got to plug in all those k values right here. You've got a 0, you've got a 1, and you've got a 2. Now, because I'm starting at 0, I don't need to plug in k equals 3, because that would give me 4 answers, and I only want 3 answers. Okay, if it said the 4th root, I would plug in k equals 0, 1, 2, and 3. But if it was the square root, what values of k would I plug in?
0 and 1.
0 and 1, exactly. Okay, so it's always 1 less than however many answers you have, because 0 counts as the first answer. Okay. All right, so let's have you guys try one with degrees. I think it'll be a little bit easier. But when we're looking at degrees, do I want to use 2 pi in my equation?
No, it's 360.
Yeah, exactly. We're going to use 360 instead of 2 pi. Okay, we use 360 when it's in degrees. We use 2 pi when it's in radians. Okay, so let me zoom out so you can see both the new question as well as the old question. All right, and looking ahead, we know that we should have 4 answers here for the root. All right, so we should be starting off with something like this. We are looking for the 4th root. So I know that we're going to have 4 answers. And if you are a fan of pre-thinking, so you kind of know where you're going to be, maybe you even write down that k equals 0, 1, 2, and 3, so you know where to stop later on. Okay. But the pattern here is we're going to raise the root or the distance to the 1/4 power. And then we're going to take our angle and we're going to divide it by 4. And we're going to take another cycle around the circle and divide that by 4. Okay, so we could think about this as like the general form. And we could certainly simplify this. It's a little bit easier to simplify with degrees, but this would be 2 times 30 plus 90k, right? And from here, we just gotta plug in 0, 1, 2, and 3 for our k values. And I realized I forgot the cis, sorry. Okay. So when we plug in k equals 0, we're going to get 2 cis 30 degrees, because that 90 times 0 goes to 0. When we plug in k equals 1, we get 2 cis 120 degrees, because 30 plus 90 gives us 120. I can do the same thing, plug in 2 and plug in 3, and I'm going to get 2 cis, what's the next angle?
210 and 300.
Yeah, I'm going to take 120 and add 90. And then I'm going to take 210 and I'm going to add another 90. Good. And so those are your 4 roots for the complex number 16 cis 120. Okay. This corresponds to our 4 answers. All right. But before we wrap up this section, let's write this formula for roots with variables so we know what we can plug in later on when we're trying different problems. So in general, z, if we're raising it to the root, is going to be 1 over n. Okay, so n is the root. If it's the cube root, then n is 3. If it's the 4th root, n is 4. If it's the 5th root, n is 5. And if it's a square root, n is 2. And the formula we can use is we take the distance and raise it to the same power. And then we have cis of our angle divided by n plus 2 pi k over n. So this is for the radians. If you're working in radians, you want to use this version. The only thing you need to change if it's in degrees is you just need to change that 2 pi to a 360. And this will give you the same formula, but for degrees. Okay? So this seems like a good place to stop and take a break, all right? And we still have one more section to cover. So I'm going to stop this video here.